Welcome to this first lecture series of game theory. My name is Revi, and my goal in the next 10 minutes is for you to understand the mechanics of Nash equilibrium and check if that's something to be made precise, is the Nash equilibrium. And the plan is we're going to start off with a definition. We're going to unpack some of the various terms that you don't understand from that definition. And then with a simple example, we're going to illustrate that concept. So let's start right away. So what is a Nash equilibrium? So what is a Nash equilibrium? Well, a Nash equilibrium, the something that we want, is a profile of strategies, where no player has a strict incentive to unilaterally change their strategy. Sometimes this is referred to as deviate. So no player has an incentive to deviate. So unilaterally change their strategy. Now, the next thing that I usually ask my students here is to ask themselves, what are the terms that they actually do not understand in this? And the thing that they don't understand is a profile of strategies. And unilateral is another one, which deserves a bit more explanation. So unilateral, let's start with a sort of easy one. Unilateral means holding other players' strategies as known or constant. Holding all other players' strategies constant or known, and known actually, and known. So what is a profile of strategy? Well, a profile of strategy is just a set of strategies, one for each player in the game, a collection or a set, if you like, of strategies, one for each player in the game. Okay. And perhaps the most important definition to try and understand Nash equilibrium, which most students from experience don't, and they're able to, they somehow struggle along through Nash equilibrium without understanding this, is the concept of what is a strategy. And that's really what we're going to be focusing on today to really understand Nash equilibrium. So what's a Nash equilibrium? It's a profile of strategy with some special characteristics. But what's a profile of strategy is a collection of strategies. So perhaps far more important than Nash equilibrium, or a prerequisite of understanding Nash equilibrium, is to ask yourself, what is, and I'm going to focus on a pure strategy first, because it's, from a teaching perspective, it's easier. What is a pure strategy? What does it mean for a pure strategy? We want to be very specific here. So a pure strategy assigns one action at every decision-making point, for all possible histories at each decision-making point. Okay, so let's try and unpack that. So similar question, what are the terms that you don't understand there? So first note that the concept of a strategy in game theory has nothing to do with your literal meaning of a strategy, doing something that's good for you. It purely assigns, so a pure strategy or a strategy assigns one action at every decision-making point. So what is a decision-making point? So that would be some decision-making point. Well, it's a point in the game where you have to make a decision. You can actually count the number of decisions that you have to make in a particular game. So a point where a decision needs to be made, where a decision is made. And then the terms that also people don't understand is, what is a history? What is a possible history? So a history, so we need to define that. A history at the decision-making point, so I can abbreviate at decision-making point, is a collection of all past actions by each player. Right? So there must be some idea that I start off with a point where I need to make a decision. So for example, decide rock, paper, scissors if I'm playing rock, paper, scissors. And a history, a possible history, is a collection of all past action by each player. So for example, if I'm playing rock, paper, scissors multiple times, a history would be what was played in all the previous rounds. And a history belongs to a particular decision-making point, right? So before you make a decision, you can ask yourself, what's the history? What do I know about the actions that were previously taken, not just from me, but from all the players in there? So what's a strategy? What's a pure strategy? It simply assigns one action at every decision-making point for all possible histories at each decision-making point, right? So this second part here is just reminding us that a history belongs to the decision-making point. So we cannot talk about what's a history in the game. We have to talk about a history for a particular decision-making point. Okay, so let's kind of look at this. So what's our goal? We want to understand the mechanics of a Nash equilibrium and check if this something now, we know it's a profile of strategies. So when someone says, is this a Nash equilibrium? They're really saying, is this profile of strategy special enough to be called a Nash equilibrium? What does it mean for a profile to be special enough? It must be that no player has a strict incentive to unilaterally deviate or change their strategy, holding all other players' strategies constant and known. The concept of a strategy is really the most important concept. So let's try and understand that with some simple rules. Let's say example one is we're going to play rock, paper, scissors, rock, paper, scissors once. Okay, well, so if you think about it, there's two players that play rock, paper, scissors. So number of players is 2. So I could ask myself, what's the number of players? Is 2. I can ask myself, what is the number of decision-making point? Well, if we play this once, there's really just one decision-making point. Players, both of them have to make only one decision-making point, right? I could also ask, what's the possible histories at each of these decision-making point? What are the histories? Well, in this particular case, the game just started, right? So there's only one history where you just know that the game started. There is no past action. So we generally call this like an empty set. There is no past actions to kind of think about, right? So if you look at rock, paper, scissors, we can also talk about, at this decision-making point, we can talk about what are the number of actions available at the decision-making point. Well, the number of actions that are available is paper, rock, scissors. So because you have one decision-making point, and because there's no histories, so the possible contingency of histories, a strategy, a particular pure strategy here, the strategy for player I, let's call it, could be, for example, paper. What's the number of pure strategies in this game? Well, you probably guessed it, is 3. So because there's one decision-making point and there's only one history, which is the game just started, here the number of actions that are available matches with the number of pure strategies. This is not necessarily always the case. Okay, let's go to the second one. Let's go to the second game. Example 2. Let's do splitting of 100 pounds. Of 100 pounds. And here's how the game would work. Okay, so both players will write down the number of pounds that they want out of that 100 for themselves, and it has to be a full number. So the possible action set of each player I would be I want 0, I want 1, I want 2, all the way to I want 100 pounds. And the rules of the game is if the action or the request of player 1 plus the action or the request of player 2 is less or equal to 100, the payoffs, so payoffs are very important for game theory. We need to have who are the players, what actions do they have available at every decision-making point, and what are the payoffs that comes out of the game. So if the sum is less than 100, player 1 will get what they asked for. Player 2 will also get what they asked for. What happens if A1 plus A2 is strictly greater than 100? They will both get 0 because they were quite greedy, right? So we have a game here, right? What's the definition of a game? It's players, it's actions available to those players, and payoffs assigned to all possible action combinations. And that we have here, okay? Now I'm going to ask you some questions to try and really illustrate the mechanics of a Nash equilibrium. I will ask you, for example, give me a strategy for player 1. Well, you could say strategy for player 1 is I will demand 10 pounds. I could say, give me a strategy for player 2. Well, you could say, I go back to the definition of a strategy. I simply need to assign an action. Doesn't have to be good at every decision-making point. I only have one decision-making point for all possible histories at that decision-making point. Well, there's only one history, which is the beginning of the game. And therefore, this thing here could be 30, for example. Now, if I collect one strategy for each player, there's only 2 players in the game. When I collect these 2 strategies, this is now a profile of strategies. Profile of strategies. Because I could go back to this definition here. What is a pure strategy? Well, we know what a pure strategy is, but what is a profile of strategy? It's a collection of strategies, but it's a special collection of strategy because you have to have one for each player in the game. So because I have collected one strategy for each player in the game, this is a profile of strategy. I can ask you now the all-important question that is this profile of strategy special enough to be called a Nash equilibrium? So I could say, is this a Nash equilibrium ? Your answer there should go back to the definition. So I go back to the definition, and this answer should be mechanical. If you've understood the definition, the answer should be mechanical. So Nash equilibrium is a profile strategy. That is a profile strategy where no player has a strict incentive to unilaterally deviate or change their strategy. So I look back here and I say, okay, let me fix this player 2, okay? And let me tell player 1 that that's the strategy. Let me make this strategy known to player 1. Note, when you play this game, and this is something that confuses students a lot, when you play this game, you actually don't know what the other player is doing. But to check whether a profile strategy is a Nash equilibrium, you do something very simple. You pretend that you know the strategy of the other guy. So now we're going to ask player 1, do you have a strict incentive to unilaterally deviate? And player 1 says, well, at the moment, I'm getting my 10. And can I do strictly better? Of course. If I ask for 20, for example, I'm going to get better because 20 plus 30 is less than 100, right? So is this a Nash equilibrium? You'd say, no, this is not a Nash equilibrium. Okay. So I could tell you, for example, what about strategy for player 1 is to play 30. Strategy for player 2 is to play, let's say, 45. Well, is this a profile of strategy? You bet it is, because it has one strategy for each player, okay? And this is a profile strategy. Is it a Nash equilibrium? The answer is no. Why? Because if you pick any player and you fix the strategy of the other, you hold constant and known the strategy of the other, the answer is No, it's not. It's not a Nash. It's not a Nash equilibrium, right? You can easily convince yourself for this. Now, here's something that's not immediately obvious. Strategy of player 1, 0. Strategy of player 2, 100. Okay, this is part of the action space. This together, I form a profile of strategy. I can ask the question, is this a Nash equilibrium? What would you say to that? So stop the video if you like and think about that for a second. If you think through this, what you really get is that the answer is yes. Well, let's kind of think about that for a second. What is player 1 getting? So knowing that player 2 is going to select 100, what is player 1 getting? Well, he's clearly getting 0. Okay. Can he do strictly better? And that's really the key bit. Can he do strictly better? And the answer is he cannot. Because if he picks a value like 1, 2, the sum is going to be greater than 100, he cannot do strictly better. Okay. So player 1, we will say, has no incentive to unilaterally deviate. Okay. Just cannot get strict payoff. What about player 2? Player 2 is getting 100. Can he do any better? Well, he can't, because the only thing that he can do is he can lower his request. Remember, he is now holding constant player 1's strategy. So we would say that this is a Nash equilibrium. Okay. Here's another one that's not immediately clear, or it requires a bit of work. 100, 100. And by work, I mean a little bit of checking. No, if you find yourself that finding a Nash equilibrium might be a bit more challenging, but checking if something is a Nash equilibrium should be mechanical. You should be able to do it if you've understood the definition of a Nash equilibrium. And that's why this video, that's what this video is trying to accomplish. By the end of this video, you should be able to, I should be able to tell you exactly whether something is a Nash equilibrium or not. So is this a Nash equilibrium? Take a moment, pause the video, think about that. Okay, the answer for that is yes. Surprising. Well, why is it yes? Well, they're both getting 0. This guy's also getting 0. So now let's say that player 1 knows that player 2 is going to choose 100. Well, can he do any better by lowering his bid? And the answer is no. I can't do any better. If I do 50, I still get 0. If I do 99, I still get 0. If I do 0, I still get 0. And therefore, this is a Nash equilibrium by a symmetric argument as well. Okay. So note, Nash equilibrium doesn't mean better, doesn't mean the best, doesn't mean efficient. It simply means that you are checking whether there is incentive to unilaterally deviate. And I hope that you found that helpful, and I will see you on the next video.